EECS 281, lecture number 22, Dynamic Programming. Our cover slide today has a picture of Richard Bellman. He's the inventor of dynamic programming. Back in 1953, he pulled this together with a number of research projects and some work there. It's a wonderful story about Richard Bellman and the way that the name dynamic programming came about. Turns out that dynamic programming is really just made up jibber jabber. He was trying to get funding, and at the time the Secretary of Defense didn't really like the word research. And so he came up with a name that sounded like something that would have to get funded. So in this case, we think of programming, obviously, in 281 as computer programming, just writing code. But this was more like television programming in terms of like the order of programs or the programs of how trains would arrive at a station. So this programming in the dynamic programming title has nothing to do with actual coding as we think of it today. And then the word dynamic was just thrown in there because it sounds great. It's hard to think of anything that's dynamic that has a negative connotation is what he thought. So he decided to go with dynamic programming, and thus we have it. The other part of the title was memoization here, and memoization is part of the technique of dynamic programming. It has to do with storing your answers that you've calculated now and being able to look them up later. So we'll look into memos. I would call them memos for short. Look into the memo and how to successfully size those things, because that's often the biggest part of it, figuring out what size your memo needs to be. Then the data kind of fills itself out if you let it. So in dynamic programming, the primary advantage of our recursive algorithms is usually we divide the problem into smaller, independent subproblems, usually in typical recursion. However, some of our recursive problems don't give us these independent subproblems. And we saw that as we looked at some of the ones in the past. We've seen Fibonacci numbers. We'll see that one as an early example here as well. And so when these subproblems are not independent, the common sort of divide and conquer that recursion often uses is not going to be successful because there's no real division. There's overlapping. So this is where DP comes in, and we've got a couple of different approaches here. We've got bottom-up dynamic programming. That's where you start calculating from the small values up to the large value that you're trying to calculate. And then there's top-down, which is where you start asking for the biggest value, and then you go calculate smaller values as necessary. To be clear, you always end up calculating the smallest values first. There's no way to get around that. It's just that in the top-down approach, the question is asking for the biggest value or the ultimate value to be calculated. And then the solution has to figure out what subproblems need to be solved to solve the bigger problem. And if those subproblems need other subproblems to be solved, top-down keeps working its way down until it finds the smallest problem that it can solve, because these recursive solutions are never solutions until they get to a base case. That's where the only thing that a recursive solution knows ahead of time comes from. It comes from the base case. So even if we're working top down, we ask for the largest answer, the ultimate answer, and then we break down into the subproblems that are needed to calculate that. On the reverse side, the bottom up side says, well, we know we can always get these small values because they're base cases. So let's start from the base case and work our way up until we get to the ultimate answer. So these are a couple of different ways to do dynamic programming. You're going to see recursive functions for top-down calls. And you're generally going to see iterative functions for bottom-up calls. You loop until you get what you want when you're working from the bottom up. And when you're top-down, you recurse until you can get the answer that you wanted. So DP can be used if you've got some large problem that can be broken into smaller subproblems. Each one of those problems looking like a smaller version of the big one. For instance, in calculating Fibonacci, if I'm calculating a particular Fibonacci number, calculating some smaller Fibonacci number is a congruent subproblem. It looks just like the other one, it just has a smaller number. So that's what we're looking for DP. And the other thing that's important, as we mentioned already, is they're not independent subproblems. They can overlap. So in the case of our early example Fibonacci numbers, we realize that when I ask for the Fibonacci of 50, that means I need Fibonacci of 49 and 48. So there's two subproblems. But Fibonacci of 49 also needs Fibonacci of 48. So then the two subproblems, 49 and 48, are there, but 49 also needs 48, so there's the overlap. So if they're not independent and they look like the bigger problem, then DP is probably going to be a useful tool. The other thing about DP is it's great in terms of time. It usually reduces the running time of recursive algorithm tremendously. Often a complete change of complexity class. Go from something that's exponential or worse to something that looks to be linear or even quadratic is not too bad. So we'll find some really fine time improvements in dynamic programming. What they do, however, is one of the common things we've also talked about in 281 is trading space for time. You're going to use more memory to save computation time. You think about how that works. If I've got enough space and I can calculate some of this work, if I just store it, then I don't have to recalculate it again. In a situation where I don't have space, then rather than, and we'll see that in project 4 here, in parts A and B, you don't have enough space to retain a distance matrix of all the vertices. So you offset that by every time I need a value, I just calculate it. So there's trading space for time. When you don't have enough space, you use more time. When you have enough space, you certainly would like to save the time. And DP does that. It uses space that, you have to have enough space available. If you have enough space available, then you can use that space to drastically reduce the time involved in calculating some values. All right. Memoization. Technique derived from the Latin word memorandum. This is something to be remembered. And it's slightly different from memorization because it's just the act of writing things down. Memorization sort of implies something that I know that I can and just instantly access. So memoization is similar to memorization, but it's used here in direct relationship with dynamic programming. It's how DP works. And this is it. The simple, drastic solution to everything that is DP is about the memo. And the way that we use the memo is right before we leave, after we've calculated some value, rather than just returning the value that we've calculated, what we're going to do is save that. So if we need to calculate it again later, we have it. Then we return it. It's really pretty simple. So we save the inputs and we save the results, right? And that's important that we save the inputs because what I really need to know the next time I call this function with some set of inputs, I need to be able to check those inputs versus the inputs I've already calculated. And if I've seen that particular input set before, then I can go look up the result. So just saving the result isn't good enough. We will also have to save the inputs. And oftentimes, because of the way that we set the memo up, the memo is going to be some block of contiguous memory, whether it's a single variable or a one-dimensional variable or a two-dimensional variable. We've got all of this stuff in place that we've stored, our results that we've stored. And so rather than explicitly saving the inputs, I can often say, well, I'm going to use those inputs to look up the value that I need. And so if I've got a table or something that's holding this information, then I can just use those inputs and not have to store them explicitly. I just say, well, if I was looking up the inputs 2 and 4 and I've got a two-dimensional table, and if I look in position 2, 4 and use those inputs as where to look up the result, then I can often save the results only explicitly, even though I'm actually implicitly saving the inputs. That's the first half, even though it happens later. The second half is whenever I'm trying to do some calculation. When I enter the function, I say, hey, have I already done this before? Let's check the inputs that I've been given and see if I've already used them before. Because if I've used them once and I write it down, then every time I try to use them again, I just go look it up, and rather than recalculating, it's there. So if you've ever calculated it once with those particular inputs, you should be able to find that when you call it again. So this is where the speed comes from. This often can be done with 3, maybe 4 or 5 lines of code. You can take something, and I could give you if by the time we get this explained, I could give you a recursive function that was exponential. And if it was a proper type function that had an overlapping subproblem set in there, you could memoize it without ever even understanding the recursive function itself. Really minor code changes. So here, again, is Fibonacci. We've talked about it before. I think it's maybe the last time we talk about it this semester. But the Fibonacci sequence, as we know, is recursive. We've got these two base cases. F of 0 is 0, f of 1 is 1. And then my recursive case is f of n is equal to f of n minus 1 and f of n minus 2. So I can always get down to a base case, and that's going to give me any Fibonacci number that I need to calculate. So if we try to find something like Fibonacci of 5, right? We know that f of 5 is just equal to f of 4 plus f of 3. And then f of 4 is just equal to f of 3 plus f of 2. And f of 3 is just f of 2 plus f of 1. And I keep working my way down. I see that f of 3, that's just f of 2 plus f of 1. And f of 2 is f of 1 plus f of 0. And lastly, I've got f of 1 plus f of 0. And f of 1 is something I already know. So I've got to work my way down here, and you see I end up with, let's still got one more case here. F of 2 on the end still needs to be f of 1 plus f of 0. So there, calculating fib of 5, I end up calling Fibonacci of 1, 1, 2, 3, 4, 5 times, and Fibonacci of 0, 1, 2, 3 times. Is there one that I missed? Maybe a fourth one in there. Right, but I've got to call these base cases over and over again. So you can see how this ends up inefficient, because I'm going to make all of these calls, and these repeated calls to Fibonacci of 1, if I was calculating that, it would be something that was expensive. But you also saw me repeatedly break down Fibonacci of 2, for instance. How many times did I break down Fibonacci of 2? Right, so I had it here, I had it here, and I had it again there. So I broke down Fibonacci of 2 3 times, and that was actual calculation. That is not a base case. That's not something that I could just get an instant answer to. I had to calculate that. Granted, it's a simple calculation. I'm going to add a couple of things that I already did. But as I take this up to higher Fibonacci numbers, Fibonacci of 50, I am really starting to get some repeated calculations over and over and over again. So this, as it stands, this Fibonacci sequence that we looked at on the previous page mathematically, on this page we can see it in very simple, quote-unquote, elegant recursive code. It's elegant because it's done in 3 lines, 5 lines if you're writing an EECS 281 exam. It's done in 3 lines, and it's all there. We've got our base case, we've got our recursive case, and this will calculate Fibonacci numbers for you until you run out of numbers, right? However, it is inefficient as all get out. We can look at this as having exponential runtime here, big O of 1.618 to the n. So this is exponential, and bonus points if you can define that 1.618 number. What is that number, and where does it come from? All right, so how are we going to improve this Fibonacci sequence? Well, here is an example of a recursive DP version of Fibonacci number calculation. On the first page, this is just the driver function. So this isn't really the Fibonacci that we're talking about. This isn't any DP that we're talking about. This is just a driver, and you can see that it starts a loop here and runs from 0 to 100, and we're going to calculate that index of fib 0 to 100. This is going to calculate all of those Fibonacci numbers. Great. Here's where the code actually kicks in. So we see the elements from Fibonacci on the previous page, slightly redefined here, so I can see my base case in line 23. Right? My base case has something in it for when I've got 0 and 1. That's sort of like my memo is set up there, but the base case is going to come out of returning values from there. So combining 23 with what we've got here, my base case falls into if something is already in my fibs array, right? And that's what this fibs array that we've declared is. If something's already in there, or if the number being asked for is 0, right? Those actually end up being my base case. So I always rant about making sure you have a base case when you've got a recursive function. And since this is fib, and we see fib calling fib down here in line 34, this is definitely a recursive function. So my base case is much harder to see in this one, I think, than any piece of code that we've looked at, because it's a combination of lookups and static declaration. So there's a lot going on this piece of code, although it's just technique laid over the previous function, right? It's just technique laid over this. In the end, it's all of this exact same calculation, all of this exact same base case. So here's the technique, right? I'm going to cut my base case in here. My base case is going to happen at some point before I make my call to my recursive case. So before 34, I've got to have a base case. And there's a few different things going on here. First and foremost, I've got to have this base case. And so I'm going to put it into this memo here. And my memo is this fibs thing. It's a one-dimensional array of integers, long longs, and we can go look something up there when we need it here. So here's where we catch our base case. If our base case, remember, is when n is equal to 0 or n is equal to 1. So if n is equal to 0, I catch n equal to 0 right there, and I return what's in fibs at 0. Great. If n is equal to 1, I say, well, n is not 1, so I'll be looking for fibs of 1 being greater than 0. In that case, I can return it here. And that's what I see in this initial setup of the fibs memo, is this array that has a 0 and 1 in it, followed by a bunch of extra zeros. That's what you get out of a declaration like this. And you see that I've got some array declared here. It's unsigned long fibs. In front of that, I've got the static keyword. And what static does when I declare a variable inside a function is it makes that variable persist. We think of variables inside of functions as going out of scope, as having a stack frame, and once that function has been executed, once it returns, that stack frame goes away, and any of the values that were calculated in there or declared in there or passed in there or whatever, they all have been wiped clean because that stack frame is removed. However, a static variable is retained for that function's use only. This isn't some other variable that anyone can access, but this static variable is retained throughout the life of the program. So every time I call this fib function after the first, it goes and uses whatever data was already in there. The first time, it does the initialization. It does the initialization that you see there in line 23. It says, give me fibs that holds size elements, and then fill that with 0, 1, 0, 0, 0, 0, 0, 0, 0, all the way up to size. That's what that has done here. So this then is how I turn around and get my base case. My base case is going to go look there. Every case tries to look there, actually, because we see that line 30 catches my base case for n equal to 0 and n equal to 1, because at declaration time, in fibs at index 1, we've defined that to be 1. So there's a value there equal to 0, equal to the values that should be returned for base cases, n equals 0 and n equal 1. After that, the other part of the question, the first part of the question in line 30 was, if what's ever in there is greater than 0. So remember, we initialize it to look like 0, 1, 0, 0, 0, 0, 0, 0, 0. So here's where the DP aspect kicks in. It says, if I've already calculated this value, then rather than calculate it again, I'm just going to look it up. So this lookup here in line 30 says, if fibs at n is greater than 0, then obviously, since I declared them all but 1 to be 0, someone has already calculated this, so I can just return that value. All right, a little bit complicated, but as I said, it is all just technique. We could have done this in a different way. You could have done this with a class and an external member variable, or if you wanted to, you could have retained this fibs array outside of the function and passed it in as a stack variable. Maybe a reference somewhere outside there. A bunch of different ways this could have been done. This way is straightforward, fast, and it shows you a new technique. All right, one other thing up there that's our primary comment, line 18. The largest Fibonacci number that fits in unsigned 64 bits. So we've got an unsigned long. The largest number that we can fit in there is fib 93. So if we try to calculate fib 94, it's actually going to overflow the 18 quintillion variable. So we can't go above that. So we've got to be able to prevent us from trying to calculate that number, right? And you can see that if n here in line 26, if n is greater than or equal to size, if somebody's asked me for a Fibonacci 94, because size is defined here as 94, if somebody's asked me for a 94, just return 0. That's going to be overflow. They can figure out how to deal with the Fibonacci that returns 0 when they thought it should have returned something non-zero. All right? Okay, so we said that we can only calculate up to 93, and then we declared this array to be size 94. This is fundamentally important to memo sizing. As we're sizing a memo, we are going to try to size this one more in the dimension of the programming, right? In the dimension of the programming here. So in this case, as I'm working my way up to Fibonacci 93, that's the dimension I'm going. I'm going from Fibonacci numbers from 0 up to that value. And so I'm going to size my memo one larger, because what that gives me is the ability to do a square brackets 93, right? Since I declared this as size 94, and I put it here in fibs as its size, since it's 94, and that means there's 94 items. And those 94 items with 0 indexing are going to go 0, 1, 2, 3, 4, ... 91, 92, 93. If I had made this array size 93, I couldn't ask for square brackets 93 without going out of my memory segment and seg faulting, right? So I need to have this go one more in the direction that I'm programming. So we'll see that as we look at all the memos throughout the rest of the day. We'll figure out sometimes the problem has some dimensions, and the problem's dimensions don't need to be expanded, but the direction of the programming does need to be expanded by 1. And that gives us the ability at the very end, see here, if someone were to ask me for Fibonacci 93, at the very end, regardless of all of the stuff that goes on between 18 and 34, you see at the very end of Fibonacci 93, it's going to return fibs square bracket 93. That's why this has to be of size 94, because 94 gives us 0, 1, 2, 3, all the way up to 92, 93. And here's where we're going to square brackets to get our answer. All right, so that's it in a nutshell. This is a very, very large nutshell. But once we've taken all the technique and all the other stuff away from it, we see in line 34, that was the heart of the previous Fibonacci calculation. Fibs of n is equal to fibs of n minus 1 plus fibs of n minus 2. That's it. We write it down in 34, and if we need to, we turn around and return it in 35, right? So that's what we had to do. That was the major change, was in our recursive algorithm, before we return, write it down, then return it. And then before we calculate, if it's already calculated, just return it. That's dp. So here's the Fibonacci sequence now this time. That was a top-down version, right? Remember I said at the beginning, if we're going to do top-down, we're talking about a recursive function. So now I'm talking about working my way from the bottom up, and I said bottom up dp is generally calculated with our iteration, with loops here. So here I've got a loop that goes from k equals 2 all the way up to and including k is equal to I, right? And this is important once again because I is what's being asked for here. And normally when I send in some n to a function, I mean do that n times. And so I go less than n here in a for loop, because if I start at 0 and go less than n, I get n executions. Here I want to actually return the one at I, and you see the very last line once again is returning what's in this f at I. So f at I is going to be my final answer, so that means I have to have this k go all the way up to and include I, so that I make sure to write something in f at I in line 6 so that I can return something from f at I at line 7, right? So if k has to get all the way up to I, so that at one point in line 6 I can write to f of I, which allows me to return f of I in line 7. Right, so my bottom up, I'm just going to start at the smallest value, and then I'm going to use previously computed values to just calculate the next value. So this one does it all in sort of what looks like, without even understanding what's going on here, in terms of our early talks in this course, how do we know the complexity of this function? Well, look at that loop. I mean, that's clearly just a simple for loop. There's no other for loops inside of it. If you look at the work that's going on inside the for loop, you see that it's a constant amount of work, 3 lookups, 1 assignment, 1 arithmetic operation. That's it. Well, I guess there's 3 arithmetic operations. Apologies. But 3 lookups, 3 arithmetic operations, and an assignment is still a constant amount of work. So the entire complexity of this function is all dictated by what this for loop is. And so we take our absolute worst case, is when k goes from 2 all the way up to and including the n that we've been given. So this looks like it's going to run n minus 1 times, which gives me a big O of n minus 1, which then simply is a big O of n. So this is a linear function. This is great. We saw that this version of the function was exponential. And now we've got a version here that's linear, very clearly linear. We've got a local variable here, and this is just a bunch of ints, right? This one doesn't go quite as high as the other one does. We could make this be unsigned long if we wanted this to calculate larger values. This one doesn't go all the way up to 93 because this uses normal ints, signed ints. You can expand this to whatever limitations that you're looking for or are available through hardware, whichever is less. All right, so we can see here that we store all of these previous values in this for loop. I take everything from k equals 2. I've already done k equals, or at f of 0, f of 1. And then when k equals 2, I can do from f of 2 all the way up to f of I. And then finally I return f of I. So that's taking care of it, because every time I calculate some previous value, I store it. And I never need calculate it again. Okay? So this is good. Say, well, what happened to the complexity discussion in the previous version? Well, hopefully, we understand that if we could do it here in linear time, in this iterative version, and I wasn't able to do it in linear time in this recursive version, I wouldn't even bother. I would always just go for the best complexity class. So you can imagine that this is going to be linear or better, but then once again, if this was better than linear, why would we bother with this version? All right, so process of elimination is going to tell us this looks to be linear. It's not a whole lot clear here, but what this ends up being is sort of even better than linear when it's applied the way that we've applied it. So let's step back one more page and look at this driver function. Driver function says start at 0 and work your way all the way up to 100. Obviously everything above 95 3 is going to get chopped off and just return 0. But because we're using the static variable here, all the time that I've calculated, so when I calculate 5, Fibonacci of 5, it's stored. Then when I go to calculate Fibonacci of 6, Fibonacci of 4 and Fibonacci of 5 are already stored because I calculated them previously. So in actuality, what this does is it takes and turns this into a constant time call. So this is a constant time call the way the driver function is applying it. The way the driver function is applying it, it says, well, ask for 5, then ask for 6, then 7, then 8, and so on, and so on, and so on. So there's always a constant amount of work to be done. If I'm at Fibonacci 27, I just go look up 26 and 25, add them together, return the value. Constant amount of work. But that's because this driver is doing them in increasing order. So in the end, I can't say that calculating Fibonacci at 27 is done in constant time. It's done in constant time from going from already having 0 through 26. So what this then does is, because I can get 27 in constant time sometimes, or other times if I were to calculate 27 from no information, it will be done in linear time. So this actually, the way that it's used, makes this calculation of Fibonacci numbers amortized constant. Because I calculate up to 50, then I ask for 51, I can just do it in constant time. But calculating the 50 wasn't cheap. So it was linear. So ends up being linear in general, this algorithm, but the way that it's being applied is amortized constant, right? So here, in this particular instance, if I was not to use the driver function on the previous page, and I said, okay, just take this function as it stands and give me fibs 27. Fibs 27 would end up recursing in here in line 34. It would recurse to get 26 and 25 and 25 and 24, and they would end up working their way back down to a base case in linear time. And this one is also big O linear. All right. You can do the recurrence relation if you like, but that's going to get thrown off by the fact that we've got this memo. And sometimes we can just look up a value and not have to do the recurrence. But this is, as it stands, used, it's a linear calculation of a Fibonacci number, which is an extreme improvement. We were previously exponential, now we're linear. That's great. All right. Change the channel. Now we're talking about the binomial coefficient. N choose m. Here's our mathematical definition of n choose m. That's just n factorial divided by m factorial times n minus m factorial. As long as n and m are non-negative integers, I can get something out of this. So here is my binomial coefficient in its simple, elegant. No, it's not that elegant, is it? This is just multiplication. This is pretty straightforward. This isn't elegant, this is brute force. Okay, great. There's a problem with this brute force, though. If we try to do this, we say I can calculate n factorial. I just take n and multiply it by n minus 1 factorial. Great. I can do that either iteratively or recursively. Doesn't matter. If I want to do it recursively, I do it that way. If I want to do it iteratively, I just take 1 times 2 times 3 times 4 times 5 times 6 all the way up to n, and I'm good. So it's pretty easy to solve for n factorial. You say, well, n minus m factorial is just a smaller number, so I'll probably just be able to calculate that too, and m factorial, as long as it's along the way, I could have calculated that. That's pretty simple. Calculate all three of those things, do one more multiplication, one more division, there's your answer. The problem, though, is integer overflow, because factorials make huge numbers. 13 factorial, for instance, can't be represented in a 32-bit integer. It's too big to get to 13 factorial. If I go to a 64-bit integer, this is talking about like my unsigned long, I can't even represent 21 factorial. That number will overflow a 64-bit integer. I say, okay, well, we'll use something even bigger than that. We'll use a big number that gives me 128 bits. 128 bits. That is a large integer. We still can't represent 35 factorial. Some of you, I know, have heard of poker. So I'm trying to calculate. A friend asked me, I need to know what are the chances of me getting a particular poker hand. I say, well, there's 52 cards, and if I take 5 per hand, then the total number of hands is 52, choose 5. Well, wait, I can't even calculate that because trying to calculate 35 factorial is going to overflow something I have. But then you say, wait a minute, there's got to be a way. There's got to be a way to calculate. That number is not that bad. I mean, if I was going to do 52, choose 5, 52 choose 5 is going to look something like this. 52 factorial, and then I'm going to divide away 52 minus 5 factorial, right? So that big number that is 52 factorial, I'm going to divide most of that out. But with this particular approach, I can't calculate it with n factorial as it is. What do we do here? Something that we love to do. We get some help from EECS 203. Look at that. There is a reformulation of the binomial coefficient, right? This is my elegant version of the binomial coefficient. This is a recursive definition. You see the elegance, right? I'm sure you do. All right, so now it turns out that I can calculate n choose m with this recursive definition. So n choose m is simply defined as n minus 1 choose m minus 1 plus n minus 1 choose m. So there's choose defined in terms of choose. Of course, it's recursive, so I need base cases. I got 2 base cases, n choose 0 and n choose n. Those are, of course, 1. You say, why, of course? Well, how many ways, if I give you a pile of n things, can you choose 0 of them? There's only one way. You walk away without taking anything. How many ways, if I give you n things, can you choose all n of them? Once again, there's only one way. You take them all. So those are my straightforward boundary cases, and I can use them with this recursive definition in the top line to say I can calculate any n choose m that I want without worrying about having to go factorial. This works for all non-negative integers n, and you're great. And m. Let's say m there because we don't want negative m's. So that's good. All right? So with this new formulation, we can then figure out how to calculate this n choose m. Here then is that very elegant recursive definition as provided a la EECS 203 and written into some nice, solid, straightforward vanilla C++ code. It looks elegant, does it not? N choose 0, that's 1. N choose n, that's also 1. Base case, recursive functions on lock, right? In line 5, I just make these 2 recursive calls, and I'm done. I say I'm done. I'm done writing code. I'm not done waiting for the output, because this is, once again, terribly inefficient, right? This is exponential at its worst. We're doing this huge 2-dimensional exponential call here. So this is elegant in code, but is not efficient in execution. So take a pause here if you're not live. See if you can figure out how to convert this to DP. I said with our top-down recursive functions, they were easy to convert to DP just by saying, rather than return some value, write it down first. Then, rather than calculate some value, look it up first and return that if it's available. So take a pause, see if you can't figure out what to do in terms of how to return something and how to look something up. Bonus points are if you can get a proper declaration of the thing you're going to use to look things up in. All right? Let's go at the binomial coefficient from the bottom up. This is 2 loops here. You see we've lost any recursive calls to binomial coefficient bottom up. Bi-coef, BU, that's what that stands for. Binomial coefficient bottom up, there's no more references to that. All I have is a couple of for loops. They're nested for loops, and you can see that the one on the outside goes from 0 up to and including m. The one on the inside goes from, at its lowest point, 0 up to and including n. And inside of them, I've got, a conditional some conjunction, some lookup, maybe a little bit of algebra, a little bit of arithmetic, but nothing here that inside of the innermost loop that isn't constant. The different branches take a little bit different time per branch, but neither of them grows when n or m grow. They always do the same amount of work. So it's constant inside the inner loop, so that I can say the overall complexity of this function is just the size of this loop times the size of that loop. And one goes up to m, the other goes up to n. Yeah, it's real obvious. This is a big O, M, N. Simple. So previously, I didn't even go into how poorly exponential this version was. I just told you that it was exponential. Here I can see something that's linear in m and n. They're just multiplied together, right? So at worst, you could call this quadratic, but it's definitely polynomial as opposed to being exponential. All right? And if I look closely, I can see those things that I saw on the other page, right? When I is equal to j, that's when n is choosing n. Or when I is equal to 0, that's when n is choosing 0. Both of those are going to give me a 1. All right? So there's my base case from the recursive definition, even though I'm solving that recursive definition with iterative code. So there's my base case, and then here is my recursive case. I see that what's that Cij is just Ci minus 1, j minus 1, plus Ci, j minus 1. That's it. Okay, well, I've got this nifty little memo here. You see this memo gets declared in line 2. This is my contiguous block of memory that I'm going to use to store my values, and rather than calculate them, I will look them up. If they exist in here, then I will use them. In the previous version, we saw we had a test. The test to say, if what's in the memo is greater than 0, somebody must have filled it out, so just use that. The way that this version is structured is, it starts out from this low, right? The previous memo was a top-down memo, right? When we looked at that Fibonacci with that memo fibs, we never knew if something, as we came from the top down, had already been calculated. We had to look to see if it was a value that was greater than 0. Here, since we're starting at 0 and working our way up, what we can do is we can always look up some value less than what we're calculating right now because it's already been filled out. So I've gotten rid of the test for checking to see if this particular portion of the memo is filled out, because the way that I use the memo from small to big or from the bottom up lets me know that if I'm calculating some value and I want to look it up in the memo, as long as I'm looking sort of to the left in concept, as long as I'm looking less than what I'm doing, the value already has been calculated. So I don't even have to make that check. I just say, go look it up, add them together. There's my new value. Line 8 and 9 done. So I've got this memo here, and you see the sizing on it is m plus 1 and n plus 1. I can do this with a vector. I can do this at execution time. I don't have to pre-declare those things at compile time, which I would with a C-style array. So C is of size m plus 1 rows, n plus 1 columns, right? And this gets back to why I declared that fibs of size 94, even though the best I could calculate was 93. I wanted to be able to, at the end, square brackets at 93. And here, just like there, when I say I'm calculating, some binomial coefficient of n choose m, when I return, I'm going to go into there and return some mn, and you see that those are actual values I can look up. So if I'm going to do something like 8 choose 6, for instance, that's one I always do an example here. If I do 8 choose 6, I want to put C square brackets 6 square brackets 8 in there. And if I had only declared these things to be of size m and n, then both 8 and 6 would be out of bounds. So once again, this is me expanding the memo in the direction of the programming. In this case, this is two-dimensional programming, right? I'm programming my way down the m's and down the n's. So I need to go farther in both the m and n direction. One more space, just to give me that lookup. So pretty clearly, you can see here the time complexity, And hopefully by now you've figured out the memory complexity as well. I've got nothing other than I and j and m and n as these local variables, and the only other thing that has any size to it whatsoever is this c, and that's of size m plus 1, n plus 1. So I can call that big O of m plus n, both in time and memory. Great. All right, so I talked about it and asked you to figure it out. I said, let's do this binomial coefficient top down and see if you could convert it to a DP version, right? And in this DP version, we already saw in that iterative version, I needed a memo that was size m plus 1, n plus 1. So here's my memo, and in this case, I wasn't doing the static trick. Here, I've taken this memo, declared it outside, and passed it in here by reference so that the binomial helper, the recursive function that's doing all of the work, can use that memo over and over again. So you could have done this with a static, or this is much more difficult as a static because then the binomial helper isn't reentrant in the sense that you can calculate and choose, I can't calculate 8 choose 6 one time and then turn around and calculate 10 choose 9 or 10 choose whatever, because the first time I entered binomial helper, if this was static here, then I would never be able to call binomial helper with different dimensions. So in this case, I'm passing it in by reference so that the setup function, this binomial TD, which calculates the binomial coefficient top down, it should be by coef TD, right? By coef TD or binom TD needs to be able to change the dimensions on that whenever someone asks for a different choose. All right, so binomial helper here, and then all of that stuff that we saw previously. Here, if m is 0 or m is n, there's my base cases. I'm going to set up 1 in my memo, and I'm going to return 1. This one, since we're going from top down, we don't know if that particular memo location is filled out. So since we filled it out with a bunch of zeros, we can then do this check in line 7. If what's in the memo at that location is greater than 0, somebody's already filled it out, then just return it rather than calculate it. If it's 0, then I do have to calculate it. And then rather than just returning this, as I had done in the previous inefficient version, rather than returning it, I store it and then return what I stored. That's all it takes. So you see that going from our previous version of this top-down version of it, we had these 1, 2, 3, 4, 5 lines of code here, right? And then now in this new version, I had to have a helper function, but I can see here's 1, 2, 3, 4, 5 of those lines there. All I've done is added this assignment to memo and return of memo, and this check to see if it's already been calculated. That's all that's really new, right? I've got a helper function that sets up my memo, but you got to set up the memo, then you do what you already were doing, but store it before returning and try to look it up before calculating. All right, here's my general approach. Top down, we say we're going to save these values as they're calculated. This is usually the easy way to write your DP functions. A lot of times before you can solve, every time before you can solve a DP problem, you need to figure out how the smaller problems are related. So usually this defining of the recurrence relationship of the smaller subproblems to the larger problem, usually that's really easy to write as a recursive definition. That's why we generally appreciate this top-down approach, because usually that's where the problem starts from. So if I've got this recursive sort of relationship problem that I can solve and I see that they're overlapping, hey, it's already recursive. All I need to do is just write it as elegantly recursively as possible and then add memoization, and I'm done. So this is nice. It also has the benefit of, because the recursive function knows what it needs, it knows the order of the subproblems that it needs to calculate them in. So it can ask for the things that it needs, and in some cases, you won't even need to calculate some subproblems. What does that mean, right? Obviously, when I'm looking up Fibonacci numbers, I need to calculate all of the smaller Fibonacci numbers. I just can't get away without it. However, in a choose situation, for instance, in a binomial coefficient, if I were to start at 8, choose 6, and realize that to get 8, choose 6, all I needed was 7, choose 5, and 7, choose 6, right? So those are the two sub-problems that I need. I can work my way down and see that I might not need every version of every value of n choose m where the values are less than 8 and 6. And so I'll show you an example of that here, right? As I look at sort of doing this binomial coefficient, here's some nice space here, and I'll use the rest of the slide in a bit. But let's figure out, if I take my m's along this axis, and I take my n's along that axis, right? I'm going to go 0, axis, I said axis, 2, 3, 4, 5, 6, 7, and 8. 0, 2, 3, 4, 5, 6. All right, so we're going to do 8, choose 6. Better if I've got a value for 8, choose 6 to make sure that I'm calculating it right in the end. So that's 8 factorial divided by 2 factorial and 6 factorial. Spoiler alert, same as 8, choose 2. All right, but as I calculate this, I end up with something that looks like, do a cross out here, I get 8 times 7 and 2 on the bottom. So this should be 28. So in the end, my answer here is 28, so that's good. I've calculated ahead of time. I know I won't make any mistakes. So we said in our recursive definition, if m is 0, regardless of what n is, the answer is just 1. So I can sort of fill these out here just like that. Because see, I'm in the m equals 0 row, and regardless of what n column I'm in, it's always going to be 1. My other base case was when n and m were equal, and so that lets me fill out this 1 column. And then it turns out that choose is not really defined for all of these things that are down here, right? Because they represent something that's unreal, right? So if there, for instance, I'm looking at this spot right here, that's how many ways can you choose 4 items when there are 0 items? That's not possible, right? Same thing with 3 choose 5, right? How many ways can I choose 5 items out of the only 3 that are on the table? Also not possible. So I'm going to end up with this lower triangle here that is empty. No problem. I've got things going on here when I've got my base case. So my base case fills out that entire row and this one value. Then the rest of it is, how can I combine stuff that's in my memo already and get new values? So it's said that, for instance here, 2 choose 1, right? So to calculate 2 choose 1, all I need is 1 choose 0, right? And 1 choose 1. That's those two things. If I add those together, I'm going to get the value for this. And this looks like 2. So you see that this 2 was calculated by summing up horizontal 1 to the left and this diagonal 1 left and 1 up. I just add those up and I can repeat that pattern throughout the entire table. I look at 3 here because I could sum this one with that one and so on. This whole row, that's pretty straightforward. 6, 7, 8. All right. How about the next row? Right? I'm going to move my way down. 1 choose 2. That's unreal. But 2 choose 2. That's 1. That's great. And I can see here I get 3. And add those 2 up. It gives me 6. There's a 10, right? Because I get that 10 by adding those 2 items. Right? Then I work my way across here. I can get 15, 21, and 28. Remember, there was our answer because I said 8 choose 6 was the same as 8 choose 2, and they're both 28. So in the end, I've already found the answer, but I have found the correct answer. The technique is working. 3 choose 3 gives me 1. There's a 4, 10. Make that an even 20. There's 35 and what's that? 56. Looking good so far. Looking good so far. I keep working my way down. I get 4, choose 1. Has anybody noticed a pattern yet here? I hope you have. That's what, a 35 and 70. Oh, come back, come back. Go away. Yeah, down. All right, 70. 1. What do I get there? That's a 6. 21. There's our friend. 56. Did I skip something here? This looks strange to me. I have done something wrong. Those two, those two, those two. No, I'm doing good. All right. Seems right. All right, there we go. So I can wrap this up with 7 and lastly 28. And so once I've filled out this table, you see that I can fill out this table with that sort of recursive set of loops from this page right here. This version right there. So I can fill this out as I work my way through the M and N, go down each row, go down each column. I would have filled out a table that looks exactly like this in my bottom-up case. In the end, I can take that and square brackets at M and N and get the answer 28. So that's how this solution works. And from a bottom-up standpoint, you see I filled out this table. However, if I wanted to go back and sort of ask myself what was needed from a top-down sort of approach. The top-down sort of approach is that, well, I'm looking for this value right here in the corner, 28. And I know that if I had sort of 8 choose 6, I only needed these two things. Right? Because 8 choose 6 needs, of course, 7 choose 5 and 7 choose 6. And those two things really only need those two answers. And so a top-down approach would only ever calculate these highlighted green values, because they're all I need to get to base case. So the top-down approach would never calculate that other set of numbers in my upper triangle. I just wouldn't do it. To be certain, if I was writing an iterative version of this, I could also get smart enough to realize I don't have to loop all the way to the end myself. But that would be just a little bit different code than we wrote. That's a task that I think you should do. See if you can write a bottom-up version that doesn't calculate unnecessary values. But as it stands, the bottom-up version that we had works just fine. It's the right complexity class. It's the right complexity class, both time and memory. It just does some work that it doesn't need to do. Whereas if I said from the top-down approach, if I was just asking for this 8 choose 6, it would only calculate those green things. And so that's what I'm talking about here when it says I may not need to calculate I may not need to compute answers to all subproblems. So the top-down approach is oftentimes preferable because it saves me calculation work. I only end up computing the needed subcases. So it makes it adaptive, and we like adaptive code. All right, now that I've marked up this nice summary slide with all of my previous work here, we still get a chance to look at it. The general approach from the bottom up is I pre-compute the values from the base case all the way up to the solution. It's usually not very adaptive because we calculate all the smaller cases whether we need them or not. All right, we'll see another example of that as well. In nuanced terms, we can say that the bottom-up DP can be used anytime top-down DP is being used. That's true. Time and space requirements for DP may become too large. So the reason why we don't do that, for instance, in Project 4, you say, well, I'm doing all of this work with these gen perms things. What if I've already calculated that one? You can have already calculated it, but it turns out that the time to look it up becomes non-constant, right? So if you had already, for instance, calculated So I say, what if my path is 0, 1, 2, 3? So if my path is 0, 1, 2, 3, I'm trying to do an estimation on the remaining 4 through n vertices. Say, well, what happens later when I try 0, 3, 2, 1? I will have already calculated that. Can't I just go look it up? Right? Or when I'm calculating 0, 2, 1, 3, or 0, 3, 2, or 0, 3, 1, 2, or 0, all of those combinations, you say, well, I've already calculated that. I could just go look it up, because the DP way would say this is an overlapping subproblem. And it absolutely is. However, there's a bunch of different things that I can do, right? There's factorial different inputs that I'm talking about, and then I've got to figure out how to look them up, right? So if my input is 0, 1, 2, 3 versus my input being 0, 3, 2, 1, I can't in constant time sort of look up whether I've done that combination. So time and space requirements may become prohibitively large because of the way that the problem structure is. And we see that in our gen-perms approach to solving TSP. All right, one more DP problem. This one is now three-dimensional, right? So we started with our sort of scalar calculation of a Fibonacci number, and we needed a one-dimensional vector to make that happen. Now I've got this two-dimensional binomial coefficient that I calculated. Now I'm trying to figure out how to calculate moves on a chessboard. And so my problem is already two-dimensional. And I'm going to be dynamic programming through my number of moves. So I'm going to have a three-dimensional memo here. And so in this case, we're going to work with the knight from chess. If you haven't played chess, the knight has a particular move rule that makes it a dangerous piece, right? Because it moves in this L shape. So you can go two spaces in any direction, then turn right or left 90 degrees and go one more space. So that means that this black knight starting in the beginning can end up in any of these shadowed spaces in one move, right? I move 2, turn right or left, move 1. That's how a knight moves. Okay? So the problem we're trying to solve is, can I take a knight and move it from the top left corner of the board to the bottom right corner of the board? And I can. I can do it in as few as 6 moves. No fewer. I can do it in more, but that's unimportant right now. We're looking at the most efficient way to get it done. I can get it done in 6 moves. The question is, how many different ways then in 6 moves can I reach that position? Because you can think, well, maybe I'll travel down first and then I'll travel across. Or maybe I'll travel across first and then down. Or maybe I'll travel across some, down some, across some more, and so on and so on and so on. So this is not a trivial question. How can I determine the exact number of ways I can move from the top left to the bottom right in 6 moves? So we're going to do this with DP and a 3D memo. The 3D is because the board is already 2D. And then the programming direction is how many moves it's taken me, right? Where am I going to be after 5 moves? Where am I going to be after, important, 6 moves? So in that case, my memo is going to be 3D. And then in the end, I'm going to figure out the total number of routes from the top left to the bottom right in 6 moves. All right? So let's examine the problem now on a real board here, or at least a corner of a real board. So I see myself here in this top left corner. That's this red knight. And I can see that after 1 move, I could either be here in this black knight or here in that black knight. After 2 moves, meaning I started in one of these 2 black positions, I could end up in any of these gray positions. Right? That looks good. It looks good. Something looks off here. Am I imagining something? No, I'm good. I'm good. Yeah, okay. Whew. All right. That's right. Possible after 2 moves. Okay. So I end up with this overlapping subproblem, right? Because if I'm trying to get to this place right here after 2 moves, that was one of the ones that was legal here. That's this position right here. So to get here after 2 moves, you can see that I could either have come from here or here. So in terms of subproblems, once I've solved this subproblem and this subproblem, I need both of them to get to solving this problem. And then if I look at how, for instance, this gray solution helps me with further moves 3 through n, I can see that if I've already solved this, it's something that I want to use later. I can reach this solution from both of these subproblems, and I need both of them. They're not independent. I can't just take one subproblem and say, well, I've got that one, that's enough for this. I need both of them. So that's why I've got this overlapping subproblem. All right? So any calculation of a partial path that goes through this gray thing could come from either of these two. That's why it's got this subproblem that's overlapping. It's not independent. So let's go back and look at that upper left corner again. Now we're taking out all the pretty pictures. We're just going to use numbers. Right? So in my memo 0, that means where can I be in 0 moves, and how many different ways can I be there? Well, if I'm starting in the top left corner, that's where I am. That's what this 1 represents. There's only one way to be at the start, and that's be at the start. Everything else that's not filled out here, just for saving visual noise, you can think of these as all being filled with 0. Because there's 0 ways that I can be in this position at the very beginning. There's 0 ways I can be here at the very beginning. So in memo 0, you can think of it having 1 in the top left corner and a 0 everywhere else. All right? Good enough. Memo 1 is how many different ways can I be in how many different places after one move. And if I start in the top left corner, I can go down 2, over 1, or I can go over 2 and down 1. And I can only be in these 2 places. And there's only one way to get there. So you can see that in memo 1, and I've kind of got this memo 0 there in gray so we can use it as a sort of a scaffold. But in reality, if it's gray or not marked, it means it's 0. So there's only 2 values here in memo 1. They're both 1s. And I just wanted to get those 2 boards all on the screen at once so we can see those 2 steps. After this, we're just going to be going with 1 board per screen. Here is memo 2, and this is showing me all of the places I can be in 2 moves and how many different ways I can be there, right? So you see my starting location now has a 2 in it because I can go down, over, and then back up and over, or I can go over, down, followed by coming back over and up. So those 2 represent the fact that these 2 1s can both access this location. So these 2 1s from memo 1 can access this location in memo 2. All I have to do is add them up and say there's 2 ways I can get there because I can come from either one of these 2 places, and there was one way to get to both of those places. You can also see that both of those places can reach this location, right? And this in indexing terms would be 3, 3. We see at 3, 3, there's 2 there as well because both of these 2 gray ones can reach there. Once again, everything that's gray or not filled out is 0 in this memo, but each one of these 1s that we see on the outskirts can all be reached by one of these 2 grays. This gray can go down, over, and hit that, down, over, and hit that. This gray can go over, down, over, and hit that. So those are all the ones there in the lower left. And then in the upper right, I see I can go over, down, over, up from that one, or I can go over, up, over for that one. All right, so there's my memo 2. Let's clean up the memo 2. So now we only see the memo 2 values. I said we're going to take those out. And from now on, I think we don't have any of our previous memos in there. We'll just go to memo 3. As we're trying to calculate memo 3, see, I'm going to end up calculating this location, which was one of my original 1 move locations. After 1 move, I could be here. Turns out after 3 moves, I could also be here 8 different ways. And the reason why that's 8 is because the previous memo, memo 2, has these values in it, 2, 1, 1, 2, 1, 1. And if I add them all up, because they can all reach this location in 1 move. So if I would be at the 2, 1, 1 or the 2, 1, 1, then I end up with 8 here by adding those all together. 2 plus 1 plus 1 is 4, plus 2 plus 1 plus 1 more is 8. So I can easily calculate this location just by looking up all of the previously calculated values, the other ways that I could get there. So to find in general terms in a DP solution, to find out how I could get to step 3, I just need to say, how many ways can I get to step 2, and how are they related to step 3? That's our generic terms. And how that applies to this particular problem is, in the 2 steps, I could get to those black values, and then I add them all up to get to the 3rd step. So I add up the 2, 1, 1 and the 2, 1, 1, and I get 8 there. You can see also that this is symmetric here, and this should still be white. But this symmetric location here has another 8, and that makes good sense. It was symmetric when we first got there in 1s. 2 moves later, it's nice that it's still symmetric when we get there in 8s. All right, so there is Memo 3 with a Memo 2 overlaid. And another thing that's starting to come clear is, if I start in that top left corner on a blue, after I move, I'm going to travel 3 spaces. 2, then 1. So I travel 3 spaces. So I start on blue, 1 move later I'm on white. If I start on white, 1 move later I'm on blue. So here you can see that my Memo 3, with the black digits on the white squares, is getting help from the Memo 2 with the gray digits on the blue squares. So I only ever need to write in on one particular color, either on the whites or on the blues, but not on both. All right? Here's Memo 4 only. And that's taking from the ways that I've got. See, it would be nice. It looks like I'm getting pretty close to this bottom right corner here. But since this is an even numbered move and I started on blue, there's no way in 5 moves that I can end on blue. Because blue goes to white, white goes to blue. So after this Memo 4, I'm still going to have 0 chance to be in the bottom right-hand corner. And we'll see that. It ends up looking something like this. And each one of these locations, right here, this 55, has been the sum of the values that were seen here, here, and here in the previous memo. Right? So if I were to take those 3 things together and say 17 plus 16, 31. Did I do this right? 17 plus 16, no, that's 33. Plus 22 more, that's 55. So adding those 3 things up were what gave me this value here, this 55. And you can pick any value you like anywhere else on the board. How about this 38 down here in the bottom? Where did that come from? That has sources that look like they could be here, 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 or here. That's where 38 could reach in one move, or could be reached in one move. To go from Memo 4 to Memo 5, this 38. If I go back a page, I see that I would just add up this. There's 23, and another 15 gives me exactly 38. All right? Drum roll. It happens. What's the answer? The answer to the original question, of course, was how many ways can I be here after 6 moves? It's pretty easy to see now. If this is my ultimate location, it can only take values from there or there. I add those two 54s up. What do I get? 108. All right, that's the final answer. That's how this works, right? And you see here that I've gone 1 extra value in the direction I'm programming. I'm programming to 6 moves, so I had to have a memo that was of size 7. So it could be index 0, 1, 2, 3, 4, 5, and 6. I didn't have to go in any other dimension because the board is 8 by 8, is 8 by 8, is 8 by 8. I don't need to go 9 by 9 to figure out how my travels on an 8 by 8 board goes. I do need to go 1 extra dimension in the way that I'm programming. That's why the memo is up to a 6. All right? So here's my wrap up. If I said, what was the time complexity for this solution, what would you say? I had to fill out these boards. Some were initialized as 0. I had to calculate some values. So it looks like, if I had to guess, that the big O of this was looking like time complexity in 8 by 8, because it was an 8 by 8 board, and I filled out 6 of them. or 7 if you consider the initialization and the start position 1. But really where I did any work was through 6 of them. So I could say that this would be 8 by 8 by 6. So my generalized time complexity, given a board of size m and a number of moves n, would just be m times n squared. What about the memory complexity? Well, pretty easily, I could just see that I used those memos, and there was 8 of those. It was an 8 by 8, and there was 7 of them, so I could get away with that as well in m times n squared memory complexity. Great. Now a question we haven't really talked about. We've just been so wrapped up in how much speed we're getting out of this DP. How about, is there a way to reduce my memory footprint? I gave you a hint on that one. I said blue only moves to white, white only moves to blue. So in order for me to calculate a particular, for instance, set of blue numbers, all I needed was the previous set of white numbers. I never even needed any previous blue numbers. So then you could think, well, it turns out I could probably just sort of toggle back and forth, adding white into blue, adding blue into white, adding white into blue, adding blue into white, and you'd be right. I could take this down from being m times n squared to just being n squared. And in reality, I could do it all in the same bunch of memory, couldn't I? I wouldn't even have to have 2 boards. I could just add the whites of one board to the blues of another board. Add the whites of one board to the blues of the next board in the same board, the next move in the same board, add them back to the whites and so on. So I could take this down from m times n squared in terms of memory. I could get this down to just n squared. And that's pretty interesting. Let's see, how can I apply that with my previous problem solutions? How about that binomial coefficient? Well, think about how the binomial coefficient worked. We were always adding the row up and over 1, and then just the one previous in the current row. So all I ever needed to fill out any particular row was the row I was in and the previous row. So instead of having this m by n two-dimensional vector for the binomial coefficient, I could actually just have 2 n size vectors. So I could reduce the memory there. And I think it's pretty straightforward how you might save some memory on Fibonacci, right? If I was really only worried with calculating one particular Fibonacci number, say somebody said, give me Fib 15. Like, okay, to get that, all I ever really needed was the previous 2 values. I didn't need the entire vector. The vector made it simple and fast to program and elegant to look at. But I really only needed two variables. I could sort of add those 2 up, get a new value, swap one out, add those 2, get a new value, swap one out, and so on. So a lot of times we can save some memory in our DP if we're willing to write a little bit more code, right? Not necessarily slower, but it would also save memory. Since this is a memory trade for time, if you end up in a situation where you would still like to make a memory trade for time, and you may have some memory constraints, sometimes you can reduce that. So how about the top-down method? That's my description here. Can you describe the top-down method? Because this was clearly a bottom-up, right? I wrote loops on these knights, and I started by filling out 0, then filling out 1, then filling out 2, then filling out 3. That's the bottom-up definition. How would you describe the top-down method? All right? Top-down method says, well, I need this 108, so really I just need to know about what's in these 2 things. And those 2 things say, well, I need only some other values from over here, and so on. So you can see how in the top-down method, the only values that I need in this memo are these 2 values in top-down. So if I've got those 2, then that's all top-down needs. I don't need to even calculate this in memo 5 if I didn't want to. So this is allowing me to speed things up. All right? All right. Let's finish this wrap up here. When good approaches go bad, when the number of possible function values is too high, obviously I talked about that in terms of Project 4, and there's too many inputs for me to keep track of all of those memoed values, right? if there's no good solution known, or it's more than a simple amount of work to look something up, then this DP doesn't exactly work for us. So if it's possible that no known solution exists, then obviously trying to DP that thing isn't going to work for you. But this is falling into sort of NP complete area. And if you want to know more about this, this is a tremendously large portion of the discussion in 477. You get into some of the real theoretical explanations of what's going on in these algorithms, and learning about NP complete, trying to remember all of the subsets of these vertices is something we can't handle. Map coloring, there's other ways that we can do this. So check that out. 477 is a great course. And my final slide here, DP is this advanced technique for solving these difficult problems. It ends up trading space for time. We save a lot of time when we use some memory, and then we look up values as opposed to calculating them, and we store values as opposed to just returning them. As long as my solution domains are dependent upon each other, I've got these overlapping subproblems, then I can use DP. We looked at bottom-up solutions. We looked at top-down solutions. Anything that's here in the slides, you should be able to write either way. So we did look at only sort of the bottom-up approach to the night moves. Study by writing a top-down solution. We didn't even write the code for the bottom-up solution of night moves. If you wanted to practice, do that. In bottom-up, we use loops. We iterate. Top-down, we use recursion, and we work our way. In both cases, we always have to solve the small parts first, regardless of the order that we ask for them in. Because without the small parts, without the base case, we've got no answer. All right. Have a good one.